We're ready. The moment you've all been waiting for is today. That's why it was so pivotal. I'm like, do I keep going with this material, or because it's kind of important to you guys to know inference for one numerical variable. So just like we did with categorical variables, right? Categorical variables, you had your quiz. I just got back today, so I have not even looked at them, but hopefully they were good and Joya was nice to you. Nah, no guarantees, right? But I'll have a look at those later today. And so we're going to keep going with inference, right? That quiz was on inference for categorical variables. Right, we started with 1, and then we moved on to 2, and then what about 3 or more? And what if I can kind of cross-section them, right? Really leveling up pretty quick there. And now we're into numerical variables, right? Which is kind of the meat and potatoes of all the analyses that I suspect you'll be doing, right? Thinking way back to chapter 1, how do you determine if something is a numerical variable versus a categorical variable? You can ask yourself, well, does it make sense to talk about the average, right? And so if it makes sense to talk about the average of something, it's a numerical variable, right? And so what does that mean? So many highlights, underlines, right? It means that we're analyzing the average, right? The average or the mean. I use them interchangeably, and there's no rhyme or reason. It's just whatever I think sounds better in the moment. So feel free to do the same. They mean the same thing. So if we go to, well, we can go to your, you don't need the solutions, but your formula sheet, right, from quiz 4, for one sample proportion, right, now we're going to do the equivalent, but for the mean, right? So now I have a sample mean, and I want to compare it to what? I want to compare it to some hypothesized mean, so some hypothesized number. And we're gonna change our test statistic just ever so slightly, right? But the idea stays the same, right? I have a sample mean, so some point estimate. How far is that from my hypothesized value, taking into account the spread of this distribution, right? And then we can build a confidence interval to see, okay, now that I know more about my sample and my population, then maybe I want to have some reasonable bounds on this thing. And let's start with the boring stuff. The central limit theorem says, CLT, central limit theorem. This is the theory part that you can kind of ignore. There's a lot of theory behind the central limit theorem, but for us, we just take the formulas and use them, but we are using the central limit theorem. The central limit theorem says that X bar, remember X bar is a sample mean. Okay. So X bar is a sample mean. Follows normal distribution. That's nice. Same thing, but different. Centered on mu with a standard error of sigma over root n. And so, okay, this is the population mean. So your sample means should hover around the population means. And if you think about it, that makes sense, right? Your samples should kind of hover around. You don't expect them to be exactly at the mean, but you do expect them to be close. Okay. And then here we have the standard error of X bar. Oh, that's going to be our spread. Now, I'm going to take us back to our formula sheet. We had two different versions of the standard error, right? We said, well, I didn't even put it on your formula sheet. Here, I'll put it in here instead. Recall that P hat follows a normal distribution centered on P, right, with a standard error of the square root of PQ over N. And then the trick that we used was, okay, well, I'm trying to figure out what P is, right? And I still don't know what P is, and Q is just 1 minus P, and so I still don't know what that is. I know what N is because I have a sample size, right? So I still know what N is. But besides that, I don't know what P is. Okay? So then what we said, depending on if we're doing a hypothesis test, okay? So for a hypothesis test, we let P be P naught. We said, fine, I'm gonna use my best guess at what P is, my hypothesized value. Okay. Which meant that, okay, this thing's gonna be centered on my hypothesized value, right? That's because it's our hypothesized value, but then that's how we found the spread as well, right? The square root of P naught Q naught over N. Okay. Or in a confidence interval, we let P be replaced by our best guess P hat because we don't have a hypothesized value in a confidence interval. And so then our best guess at P is our sample proportion. Okay. Now we're going to do the same thing. Okay. Because what's the problem here? We don't know what mu is. Okay. And so we're trying to figure out, right? I try to use my sample mean to try to learn about my population mean. That's my ultimate goal. Okay. And so, but I also don't know what sigma is. Do you remember what sigma is? It's the population standard deviation. Okay. And so here, sigma is the population standard deviation, which I also don't know. I have a pretty good guess that I could use, which is the sample standard deviation. Okay. I do have my N because I chose a sample size to collect, right? And so I do have my N. But now we're going to say, okay, in place of mu, I'm going to use X bar. And in place of sigma, I'm going to use S. Which means I'm using estimates for two things. So here, we use mu equal to X bar as our, and I'll do both, and sigma equals S, the sample standard deviations, as our best guess, right? As our best guess. What's really, really nice is notice here we had different scenarios depending on if we did a hypothesis test or a confidence interval. I'm not making that distinction here. And that's really nice because that means that overall, we're just always going to use X bar, or I guess one distinction, or mu naught, depending on the situation. But I haven't introduced mu naught, so, but you can kind of guess your way there. I think your hypothesized value for the mean. So we use an estimate for mu and we use an estimate for sigma. And what happens is we kind of end up taking this normal for a ride in the way that, okay, so we're estimating mu, but at the same time, so now I'm rubbing my stomach, and then I'm also estimating sigma, so I'm patting my head, and that's the t distribution. Okay? And so the t distribution can kind of handle those two estimates being thrown at it. And so that's why you've seen the t distribution when you're estimating means instead of the z distribution. Okay? It's also the reason we start with proportions, even though they're kind of boring, because we have this kind of solid z distribution that we can start with. But now we're ready to introduce the t distribution. Okay? So since we need to use estimates for both mu and sigma, we introduce the t distribution. For means. Now, a couple of things about the t distribution. The t distribution depends on your sample size, and the shape of the t distribution is generally like the normal distribution. But the shape of the t distribution, the shape of the t distribution depends on the sample size. Why? What would that be? Which is our n, right? We'll go back here. My mu, right, or my x bar, if I have a small sample size, then I'm not very sure of what my x bar is, right, or how representative of mu it is. So I have a larger spread on my x bar. Then if I increase my sample size, right, then I have a more reliable estimate, right? And so things kind of tighten up. And same thing for our standard deviation, right? If my standard deviation comes from a large distribution, then that's relatively stable. It's a reliable estimate, as opposed to if I'm taking from a small sample size, then I have this kind of unreliable estimate, and I have more spread around my standard deviation, which is a weird concept. Don't overthink it. You can also have a look here, right? The standard error of x bar is the spread around x bar, right? And so here's our point estimate, right? And the standard error of the point estimate, which is just the spread around my point estimate. Notice how it's going to tighten up as we increase our n, right? If I take the square root of a larger number, it still becomes a larger number, right? Just not as fast. And if I divide by a larger number, I get a smaller number. Right? And so as my n increases, the standard error decreases. Okay. So in the standard error of x bar equal to, I'm going to start writing s over root n, just because that's the one that we use in our formulas anyways. Technically it's sigma, but we've replaced it with s as my best guess. Notice that as n increases, the standard error of x bar decreases. so how do we communicate the sample size to the t-distribution? Now, the t-distribution still looks like a normal distribution. General t-distribution. It's still unimodal, it's still symmetric, it's still centered at 0. It's just that depending on the sample size, the area in the tails is going to be thicker for small sample sizes. Okay. Then we have to think about, okay, well, what does the area under the tail mean? The area under the curve is the probability of this thing happening. If I have left more room in the tails, it means that, okay, I'm not very sure about my estimate. I'm allowing for kind of a bigger spread, kind of larger deviations than I normally would, but in the normal distribution. I know, far-fetched. Right, and so then for small sample sizes, we're gonna have quite thick tails. But then what happens is, as you increase your sample size, then the tails press down onto the axes. And if you think about it even further, as your sample size approaches the population size, it will become the Z distribution, right? Because then it's stable. That's not really, going to have an impact on us, but they do eventually meet once you've sampled the entire population, which is very unlikely, right? Then you can use a Z distribution. But so here, for small sample sizes, there is more area in the tails, I guess I should say. Right. Since our estimates are less reliable. Since our estimates are less reliable. But then as we increase our sample size, then these tails are going to press down, and they still go to negative infinity and positive infinity in theory, but they become the normal distribution. And so how we communicate the sample size is through the degrees of freedom. We've already seen degrees of freedom for the chi-squared, and I secretly suspect you've already heard of the degrees of freedom, maybe in your chemistry course or something like that. And so, but now we get to see it for real. Fun. So we communicate the sample size to the t-distribution, using the degrees of freedom. I guess I did write it out once, but degrees of freedom, which we abbreviate to, yeah. Now for one sample mean, I only have one sample size, and so then my degrees of freedom is n minus 1. You don't need to worry about why is it n minus 1. Don't think about it. It's actually kind of a deep rabbit hole. It's because you're estimating two things, so you'd need to know just one of them to figure out what the next one is. Ugh. Nah, just it's n minus 1. and I'll put that on your formula sheet. Okay, now I've kind of queued up, well, I queued up an example that I like to use, but nope. No. Here, let's have a look. Because the difference is arguably minimal. Okay. Here, the normal is the Z distribution. Okay. If I have 1 degree of freedom, what's my sample size? I have a sample size of 2. If the degrees of freedom is n minus 1, then I just add 1 to my degrees of freedom to find my n, right? And so this means that I have a sample of size 2. If I gave you a sample of size 2, I think your gut reaction would say, oh, this is not going to be very reliable, right? I'll do my best, but the results, you shouldn't rely on these results, right? And so that's what the t distribution says as well. If I have 2 degrees of freedom, then I have a sample of size 3, still very small. Right? Even 5 degrees of freedom, I have 6, and even at 10, I have a sample of size 11. Whereas at Z, technically, n is infinity, right? Or the population size. Notice how similar these are, right? So here, if I zoom in, I've got this thick line. That's my Z distribution. It's the closest to the axes down here, right? So the shape is very familiar to us, right? And the lightest shade one here, I'm zoomed in, so my dot's huge, is at 1 degree of freedom, so a sample of size 2. So when I say there's lots of room in the tails, it's not, you know, a crazy amount. It's just saying that, okay, a t of 5 with only 1 degree of freedom is not that extreme, right? Taking us back to a z of 5, right, we know is extreme, right? And you would probably reject H naught. And so that's what lets us kind of determine, right, is the area in the tail, the p-value. And so, but notice how it kind of shifts down towards the Z very, very quickly, right? Even at my sample of size 11, right, a sample size of 11 is still really small. You would probably aim for something higher, right? It's relatively close to the Z distribution, and up here, the total area under the curve is still 1, right? And so if I've made more room in the tails, then the peak is kind of pressed down, and then as I push my tails down, then my peak goes up and it becomes a normal distribution. So, but Excel is going to handle all that for us, which is nice. Quick. Zoomed out like that, they look basically the same, right? And so what we need, right, for a Z distribution, we had to know the mean and the standard deviation to determine the shape, right? Whereas a t, we only need to give it the degrees of freedom, and then it'll give you it will know the shape, right? It'll be centered on 0, and it'll determine the area in the tails by the degrees of freedom. In Excel, now I t.dist, I'm assuming. You give it a t, and it needs the degrees of freedom. And that's going to give you the area to the left, as always. Right. same as norm.s.dist, t.dist takes a t and the degrees of freedom and returns the area to the left, area under the curve to the left. And t.inverse takes the area to the left and the degrees of freedom and returns a t. Let's call this p, right? The p-value area to the left, if it's negative, takes p and the degrees of freedom and it returns your t. You can play around with it. I'm going by memory, so I reserve the right to fix this a little bit later, but that should be it. You don't have to memorize the commands. You just need to kind of know that they exist and start typing and see what it comes up with. Right? Okay. So, in terms of the conditions, let's get those out of the way. The conditions for the t distribution are way more relaxed than the conditions for the normal distribution for proportions, which makes sense. It was kind of a far-fetched idea, in my opinion. Anyways, it works, of course, and that's what's so cool. But we had to check a lot of conditions, right? The success-failure condition, your independence condition, all those things. Now, for the conditions, what's really neat is you can analyze the average from a skewed distribution. And that's a little bit backwards, because way back when we said, well, if you have a skewed distribution, then the median is the more appropriate center of, or measure of center, right? We said, okay, the mean is pulled in the direction of the tail, and so then we should be using the median as our measure of center. However, now, in theory, I have a collection of sample means, and they're going to be centered around the population mean. And those will be normally distributed around the population mean. And so as long as you're not pulling from a very, very, very skewed distribution, we can use the t distribution, which is kind of weird, but true. But first, we need our go-to condition, which is the independence condition. And all that's saying is that all my observations, I have to be able to assume that they're independent of each other. Okay? Can't have them kind of hinging off of each other. Whether that's true or not doesn't really matter. We have to assume that it's true, that they're independent. And so one way to ensure that is if I've randomly sampled, right? Randomly sampling ensures that we can assume independence. Randomly sampling ensures we can assume, the observations are independent of each other. That's the same condition that we've had all along, right? We have to be able to assume that these things are independent of each other. Now, do you like the sample size condition or the normality condition? You can write down both, but they are going for the same thing. I like to call it the normality condition just because it emphasizes that, okay, then I get this beautiful distribution, but the normality / sample size condition, that's that big one that we used to check, right? At least 10 expected successes, at least 10 expected failures, or observed Now, it's going to be quite a bit simpler. If our sample size is bigger than 30, we'll use 30 as kind of a benchmark. Although I've seen reports say 20. That's a little bit of a stretch in my opinion, but we'll use 30. If the sample size is larger than 30, you can go ahead and assume that this condition is satisfied. So there's kind of two phases here. If n is greater than or equal to 30, right, we can assume normality. Which means we can go ahead and use the t-distribution and be happy. That's a really kind of quick and easy set of conditions, right? As long as your sample size is bigger than 30, then things have stabilized and you're good to go. If n is less than 30, we know that, okay, and this 30 is flexible. Okay? But it's nice to have kind of a line in the sand, so to speak. So if your sample size is less than 30, which can happen, right, happens often, okay, then we need to do a little bit of work. Okay? Then we can look at the histogram of your sample, right? If it looks approximately normal, then you can assume normality. Okay? Or if for some reason you're unable to do that, I'm going to write that one down because that's the one that you'll be able to do, right? If you're unable to do that for some reason, then as long as you're able to argue that, okay, my sample came from a not very skewed distribution, right? And I'm assuming there are no extreme outliers, then I can assume normality. Okay? But let's just do the histogram way because that's how you're going to check it in real life. Okay. So, and it doesn't hurt to check it if your sample size is larger anyways, right? It doesn't hurt to make a histogram of your numerical variable, make sure it looks normal. And I know what you're thinking. Wait a second, we've done that before. I know. It's almost like I was priming you for something. So you make a histogram, seems reasonable enough. And if it looks approximately normal, then you can go ahead with your t distribution. So if the sample size is less than 30, we can make a histogram of our observations. And as long as the distribution looks approximately normal. Now, this is where we kind of, depending on how not normal it looks, we get a little bit flexy, right? And you can say, I don't know, I think if I collected more data points, it would start to look like a normal distribution, right? You're kind of talking your way into this condition, right? And so just remember that. And so we can make a histogram of our observations, and as long as the distribution looks approximately normal, the condition is satisfied. So that's nice. No crazy conditions here. Just like on this last quiz, I'm not going to make you check the conditions, right? Because it's a lot of memory space. It's more of a sit down and on an assignment type of deal, right? That you're going to check the conditions. And so on I guess next up is the final exam. Ooh. I know we're on a downhill roller coaster. Yeah. Yeah. Yeah, next up, final exam. I'm not going to make you check the conditions, right? You'll have bigger fish to fry. And so, but I will make you do an assignment where you have to check the conditions. Ask me if I've made that assignment yet. No, but I will. I promise. Or there they are, the conditions that you should be checking. Okay. So now we're ready. Conditions out of the way. I tend to call that step 0 because I always skip it, right? But let's get into what does a hypothesis test look like for a one sample mean type of question, right? And so I'll ask you what type of question it is, right? And that's really to point you in the right direction of, okay, then I need to be here on my formula sheet, and then I'm really focused, right? And as long as you stick with it, right, then you're okay. So this is for a one sample mean. One sample means I only have one sample that I'm interested in, right? Your data set likely has more, right? But what it means is I want to compare my sample mean to some value. Okay? And so for a hypothesis test, let's start there, just because that's the money maker. Right? We do a hypothesis test because I have some idea about how my sample mean compares to some hypothesized value. Okay? My null hypothesis has to be about mu, right? Has to be about the population mean because I'm using my sample mean, but really I'm trying to learn about my population mean. And how does it compare to some hypothesized value? Now this value, mu naught, is the value we want to compare our X bar to. Right? It's going to be from the question or your research question if you're constructing it yourself. Your alternative hypothesis, I'm not going to jot it down because it has to be about mu and it has to be about how it compares to mu naught. And then you've got options, right? If you want to know if there's a difference between your mean and your hypothesized value, right, then you'd have not equal to. You could talk about if it's less than or if it's greater than, but it's always safest to use not equal to. But sometimes I make you kind of practice one-sided tests like I have in the example coming up. So what do you need to do a hypothesis test? You need to know, well, what's my hypothesis? And what's my test statistic? And so my test statistic, remember, any test statistic is going to be your point estimate minus your hypothesized value divided by the standard error of the point estimate. That's been the setup all along. I know it doesn't feel like it, but it has been. So we were calculating Zs, but now I know that, I'm going to have to use an estimate for my mu, and I use an estimate for my sigma, and that makes a mess. And so I have to use a t distribution. Right? The t's can handle it. And the t's are just more flexible than the z's. My point estimate, my best guess at what the mean is my x bar, right? My sample mean. how far is it from my hypothesized value, mu naught? Taking into account the spread of my point estimate, which is the standard error of x bar, which we just said was s divided by root n. So your t is going to be calculated this way. Then, knowing that you have a t, you use the t distribution with n-1 degrees of freedom to find the p-value. Right? But the p-value still behaves the same. It has to match your alternative hypothesis, right? And so if your alternative hypothesis, and then to find, I'll write it out, the p-value, we use the t distribution, with degrees of freedom equal to n-1. And we've seen it before, but I really don't think it hurts to see it again, potentially in new light, just because you've worked with it now, okay? But your p-value is going to depend on your alternative hypothesis. So if mu is that mu is less than mu naught, right? I'll try to sneak it in on this one page. Then my x bar would be here, and my one-sided p-value is the area to the left. Right? I can only use something that's smaller than my mu naught to prove that it's significantly smaller than mu naught. Right? So that's how I know it has to be in the lower end. Okay. Versus if my alternative hypothesis is that mu is greater than mu naught, well, then I know that my x bar should probably be above my hypothesized value. And then the p-value, the probability of seeing something as extreme or more extreme, assuming the null hypothesis is true, is going to be in the upper tail. And then the alternative is that mu is not equal to mu naught. Then your sample mean is allowed to happen in either tail. In fact, we're equally concerned with either tail. Now, it's only going to appear in one of the tails, and that's why we replicate it in the other tail, because we would be just as concerned with the other tail. I can't remember exactly, but maybe the t distribution in Excel, it might have a two-tailed option, right? Which would just take the one-tailed p-value and multiply by 2. I can't remember exactly, but worth poking around with. Okay. Once you have your p-value, right? So from your test statistic, right? Then you have to find your p-value, but then your conclusion stays the same, right? If the p-value is small enough, you have enough evidence to reject H naught. Right? If it's not, you don't. And so from there, the conclusion stays the same. Right? So in terms of how we've been labeling our steps, right? This is step 1. This is your step 2. And then finding the p-value is your step 3. And then step 4 is your conclusion. You don't have to label your steps, but it's nice to have a little guide. If you have now found that x bar is significantly far enough away from mu naught to reject H naught, then usually what we want to know is, okay, well then what is a reasonable value for x bar, or what are some reasonable values for x bar? And so that's when we start building a confidence interval. So the confidence interval, in general, what did I use? In any confidence interval, you have your point estimate plus minus some critical value times the standard error of the point estimate. That's any confidence interval. In this case, my point estimate is X bar. My critical value is, instead of a Z star, it's going to be a T star, okay, with n minus 1 degrees of freedom. And it's the T that captures the central 95 or 90 or whatever percentage of the curve that you're trying to build a confidence interval for. Okay. And so here, I'm just going to write T star. And then the standard error of the point estimate, unlike the proportions, it just stays the same for both the hypothesis test and the confidence intervals for means. And so that's nice. So times S over root n. I think I remember seeing, maybe Sydney had it written out a little bit differently, T times S over root n, something like that. They're the same, right? I'm just multiplying and dividing. The reason I like to write it like this is just to emphasize that it's still taking this form of the critical value times the standard error of the point estimate. And I like to kind of keep them separated. Right? But you can write them however you want, right? It's just multiplication division. But you're not allowed to cross this plus minus. That's the same for all of us. So here, let's talk about what this is. My T star, my negative T star and my positive T star, all right, is what captures my confidence level. The central 95% of the curve, for example. Right? It's going to depend on the degrees of freedom again, right? But so for example, 95%, right? The central 95%, which forces 5% in the tails, but split evenly between the tails. And that's how you find your T star. Okay, so a little bit more work finding your T star, but the theory is the same as your Z star, right? It's just that Zs were fixed. Your interpretation for your confidence interval stays the same. We're 95% confident that this interval that we've built captures the population mean of whatever you're talking about. There. Now you know it. Now, let's do an example. And I'm pretty proud of myself because this is actually the example that I always use for one sample means, but it just happens to be water related. I know. Wow. Just wow. Oh, yeah. And I usually show this around this time in the course. If you don't know what a p-value is, it's okay. What I'm expecting of you, and I know it feels like, oh, yeah, if you're feeling like, wow, I should probably know what a p-value is, that's where I want you to be. I think that's a reasonable place for you to be in right now. I should probably know what that is. I don't get it, but it's okay, right? That's where I'm expecting you to be. So just keep at it. And one day One day, yeah, when I saw that, I was like, oh boy, yeah, I have to put that in. It is perfect. It is perfect. You know what? I'll put it in our notes even. How about that? Because I you can ask and you can keep asking. And you know what the total bummer is? I'm just going to keep saying the definition. I know, rude. But one day, right, it'll click. What is the p-value? It's the probability, which is an area under the curve, right, of seeing something as extreme or more extreme than what you saw, assuming the null hypothesis is true, right? Which means that these are all centered on what? They're all centered on mu naught, because my null hypothesis was mu is mu naught. So assuming that that's true, then what's the probability, the p-value, of me seeing an x bar way down here? Right? That's the p-value. It's easy, guys. No, it's not. It's very difficult. Okay? And this is, and I'm sure I've already confessed it, but in my first stats course that I took, it was not until I was studying for the final exam that I was like, aha, okay, now I get it. But then everything just kind of flows from there, right? And so you just need to kind of stick with it. It doesn't have to make sense. Just keep at it. And one day, hopefully before the final exam, you'll have your eureka moment. And then you can text me and tell me. Okay? But until then, kind of expecting you to be aware of p-values, and they are something we use and something you have to do. Okay. Where's my example that I'm so proud of? My example that I always use is here. Let me pull it in. Now, the problem is you guys are going to be able to tell me if this is true or not. And this is where I say I stole it from a textbook, so you can't come at me. I don't just make these things up. Maybe it's true, maybe it's not. Maybe it's Maybelline. The level of dissolved, oh, I guess I should label it as an example. How much time do I have? Oh, pretty good. Nice. Phew. Got the gift of gab. I do. The level of dissolved oxygen, DO, in a stream or a river is an important indicator of the water's ability to support aquatic life. Please remember that. I tell this to all my other classes, so I hope it's true. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. 15 of them. Obviously, this would just be one column in an Excel spreadsheet, but that doesn't really play nice with this slide, so it had to be listed like this. And we're told that the mean and the standard deviation of this sample, okay, so that's how you know that, okay, this must be an X bar, right? Even if it's not labeled as X bar, if it's a mean from the sample, it has to be an X bar, is 4.77. And the standard deviation of the sample, making it an S, is 0.94. And so we're given that information. Relatively easy. If I gave you this in a spreadsheet, right, you can calculate the mean and the standard deviation, but those would be sample means and sample standard deviations, right? And so just keep track of those. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Dun, dun, dun. Maybe 5 is, I don't know. Like I said, I just stole it. But I'm proud to have it. Is there evidence? Tells me we need to do a hypothesis test. Right. Whenever you need evidence for something, right, then you have to do a full-blown hypothesis test. Well, just for an example, let's check the conditions. Okay. I'll call it step 0. You don't really need to do it on the final exam, but here we are together, so why not check the conditions? Oh, I hear it. I need a remote control. Okay. So we're going to check the conditions. Well, first, let's talk about what type of question it is. What type of question it is. From today on, right, you're going to have kind of a branch of 2 paths that you can start, right? It's either categorical data, which means you're going to analyze the proportions, just like you were doing on quiz 4, or it's numerical data, which means you're going to analyze the means, right? And that's going to take you down the path of your formula sheet, I guess. Yeah. So we have, this looks like numerical data, right? But there's also some other clues, such as I give you the mean and the standard deviation, right? Whenever there's a standard deviation involved, it's going to be a numerical variable, right? We can't calculate the standard deviation of a categorical variable. So those are kind of my clues. If I have a mean and a standard deviation, then I'm leaning towards a numerical variable or a means question. Then the question becomes, okay, do I have 1 sample, or you guessed it, eventually we're going to have 2 samples that we want to compare to each other. And so, but for today, we just have 1 sample. And so this is a 1 sample mean type of question. All right. Some clues were that we were given 1 X bar and 1 S, right? And 1 sample size. I guess I can add that in. Oops. And 1 N, which is kind of the 1 sample mean. What do we want to do? We want to compare 4.77, right, to 5. 4.77 is less than 5, right? We're concerned if it is significantly less than 5. Right? We expect our sample mean to kind of be hovering around our population mean, but if that population mean is showing kind of significantly less than 5, then that's trouble, right? So let's briefly check the conditions. The first condition is independence. Now, we are told that these were randomly chosen locations, right? And so the sample was randomly selected, and so we can assume independence. Oh, whoops. that's not what I wanted to do here. There. The sample was randomly selected. So we may assume independence. How about that normality condition? We use 30 as kind of a cutoff. If it's more than 30, we can just go ahead and assume the normality condition applies. Now we have a sample of size 15, right, which is up here. You can count them, or it says at 15 randomly chosen locations. So that's less than 30. Okay. So we need to talk our way out of it or into it, depending on how you think about it. The normality condition n is 15, which is less than 30. We could make a histogram of this and make sure that it looks approximately normal. I probably should have done that, but I'm not going to enter all those data points now and make a histogram. That's not really worth it. But we assume that a histogram would look approximately normal. How about that? We assume a histogram of the observations would look approximately normal. Another way you could argue it is, okay, is there any reason to think that different parts of the stream, right, would generate a skewed distribution of dissolved oxygen levels, right? Or are they kind of relatively even throughout the entire stream? Now, I don't know what the case would be, okay? But I assume that it would be relatively well mixed throughout the stream. And so then there's no reason to think that I'm pulling from anything but a normal distribution. And so maybe I will write it down. Alternatively, or we could argue that the dissolved oxygen levels in the stream follow a normal distribution. If I'm pulling from a normal distribution and I pull a mini version of it, I expect it to also look normal. Okay? And so we're kind of using that in reverse when we make a histogram and check that it looks normal, then we can assume it came from a normal distribution. But ultimately what we're doing is we're saying, okay, the population follows a normal distribution, and so we can go ahead, right? But effectively what we end up using is we make a histogram of our observations and then argue that it looks approximately normal, and then that implies that it came from a normal population. Okay, conditions. There. Therefore, the conditions for inference are satisfied. We move on with our lives. And this is where we pick up, right? On the final exam, I'll say you may assume the conditions for inference are satisfied. Great. Okay. We wanted to do a hypothesis test because we want to know, is there evidence, right, that the aquatic life is at risk? What does it mean for the aquatic life to be at risk? That's if the average dissolved oxygen level is below 5. And so that gives me a clue for my null hypothesis. So my step 1 is to state the hypotheses. Null hypothesis has to be about mu, right? I'm using my sample mean, but really what I'm trying to get at is the population mean. And so I hypothesize that mu is 5. I have to assume that it's 5 until I have proof otherwise. My alternative hypothesis, right, so now my mu naught is 5. Right? So what happened here is mu naught is 5. But I grabbed it from the question, and that's the value I want to compare my sample mean to. My alternative hypothesis has to be about mu and how it compares to 5. And then the sign here, which we've had some good practice with, right? If it's below 5, right, then we're in trouble. That puts the aquatic life at risk. And then we want to know if the aquatic life is at risk. So less than 5. This is one of those instances where we're actually hoping that we can't reject H naught, right? We're hoping that we won't have enough evidence to reject H naught because this would be really bad, right? The dissolved oxygen level is less than what we want it to be. And so then we're in trouble, right? And so this is one of those scenarios where we're just doing this testing to make sure that it hasn't changed significantly from 5. I assume that something higher than 5 would probably also be bad, but I don't know. So I'll just use the question as it is, but making it a one-sided test, right? I'm only concerned with this one extreme, right? And so now we're doing this testing just to ensure that everything is all good, right? But we have to do it in case it's not. This makes it a one-sided test. I'm only concerned with the one extreme. You don't have to write down whether it's a one-sided test or a two-sided test, but it's a nice reminder because you don't use it until step 3. And so it's nice to kind of jot it down early. Step 2, do the test. Calculate the test statistics. So boring. I like do the test better. Do the test, do the do. Now our test statistic is a t, which is why it's called a t-test, right? Usually in industry, oh yeah, I just ran a t-test and, well, you just did a hypothesis test where you calculated a t and that's all you're saying, right? So it sounds really cool, but it's, you know what it is now, so you can sound cool too. Oh, and then I'll run a t-test, I think, right? As long as you're talking about an analysis about means, right? Otherwise it's a z-test, right? Most of the time you're analyzing means, and so you're going to do a t-test, right? And so here, this is why it's called a t-test. And that's kind of all encompassing. It's a hypothesis test about a mean, and you calculate a t as your test statistic. T in this case is x bar minus mu naught. How far is my sample mean from my hypothesized mean? Taking into account the spread of S over root n. just like our Zs were, we used a Z for one sample proportion and two sample proportions. It was just how we got our Z changed. We're going to see that with the T statistic as well. We're going to be able to calculate a T like this, but then we'll also be able to build it out to comparing two sample means, but we'll still end up at a T, and then we're back to where we're going to be here. Right? And so that's really nice when we can use the same test statistic in different scenarios, right? One that we know. Okay, so for us, our T, X bar was 4.77. 4.77. How far is it from 5? Taking into account the spread. Right? Divided by S, which was 0.94. Divided by the square root of n, which is 15. We'll do these on the sly here. 4.77 minus 5. I'll show some work just in case. Negative 0.23 divided by 0.94 divided by the square root of 45, no, 15. 0.2427069564. Negative 0.23 divided by that, I get a T of negative 0.9476448,613. This is a good thing. This is not very far away, right? What is this saying? This is saying that 4.77 is 0.948, let's say, standard errors below 5. Not very far. Even using our Zs, right, which are going to be the strictest in this case, right, compared to Ts. Ts have a little bit more wiggle room, especially at small sample sizes, right? And so we definitely don't expect to reject H0 because I'm kind of hovering around the population mean or the hypothesized mean. Yeah. And so now, for step 3, which is find the p-value, we need our degrees of freedom, which is n minus 1, which is 15 minus 1, which is 14. But besides that, our p-value is going to come from the t distribution, right? So that's what's nice about the t distribution. T is still centered on 0. And we found our calculated t is negative 0.9476. Let's do 4 decimal places. So here, negative 0.9476. There. T is still going to have roughly 3 standard errors, right? As long as our sample size is big enough on either side before we are way into the tails. And so roughly 2 is still our guide, right? But we use the p-value to get a more appropriate estimate for the probability. But this area here is our one-sided p-value. I expect that to be quite large, which again, right, and that's because my t is not very far from 0. It's below 0, but that's okay, not very far. And so here you could implement the critical value approach and say, fine, I'm going to find the t where I have to cross this line in order to reject H naught, right? Which is going to correspond to an area in the tail of alpha, which is 0.05. Right? And so this could be some t star, right? A little bit different from the confidence interval, but linked. Okay? And so, and it is a critical value. And so what you could say is, well, my t hasn't crossed this point, right? We'll find the p-value just to make sure, but I suspect that my area in the tail is going to be more than 0.05. So let's use Excel. Let's see if I have it. I don't think I do. I've just been adding to random sheets and it's going to make a real mess. Or I just delete them all and never think about it again. That's an option too, and that's starting to feel pretty tempting towards the end of the course, or the end of the term. Start fresh. Okay, let's see what comes up if I go t dot dist. Aha, I knew it. I've got t dot dist regular. I've got t dot dist dot two tail, which is going to be in both the tails. That's nice. All right. We've got t dot dist dot right tail. That's nice. That means you don't have to do the 1 minus. Right. And so for a positive t, you would have to do the 1 minus trick. All right. And then you've got the t inverse, t dot inverse two tailed, and the t dot test. Ooh, that's juicy. I'll save that for next week. Yeah. You can see that the t distribution is used a lot more frequently than the norm.s.inverse and norm.s.dist, right? We've got the two tail, the right tail, all those things. Right? And so t.dist, it needs x, which should probably say t, but that's okay. Who am I to say? Negative point, now I don't remember what it was. 0.9476. 0.9476. I need my degrees of freedom, which we found was 14, right? 15 minus 1. And cumulative will always be true, just like the normal distribution, right? Because we always want up to and including that point. So here, this is going to be true. Oops. Okay. Enter. Go. I'll take a screenshot, which may be loud or may not be. Just tiny this time. It's probably always tiny in this room, but I can never remember. Tiny sound is what I mean. Oops. Crop this up. Nope. There. This means that the area in the tail is 0.179702. Right? So that means that our one-sided p-value, this area is 0.179702. Bless you. So now I have my p-value. Right? And just as we suspected, just using 2 as a guide, right? -2, roughly, right? 0.05. What could we do instead? let's go back to Excel. We could say, okay, how about equals T dot inverse? T dot inverse. And I'm going to force the area in the tail to be 0.05. And it wants to know my degrees of freedom, which is still 14. This means, and I'm going to screenshot this again. Where's my pictures? This means that my T, right, area of 0.05 into the tail, the T that makes that happens, right, the T dot inverse tells me, okay, I give it the area in the tail and it returns the T that makes that happen, right? We could use that in terms of our conclusion as well. I'm going to encourage you to use the p-value, right? Because it's considered more formal, but we're doing the same thing, right? We're comparing, okay, is this area less than 0.05, right? Or alternatively, what we could say is, well, I could compare my T to this critical value, right? And if it's past that point, meaning it's bigger into the negative tail in this case, right? Then I would have enough evidence to reject H naught. We prefer to use the p-value approach, right? Attaching probabilities to sample statistics. It just sounds a little bit more formal, but we're doing the same thing, right? If this T is beyond that critical value of T, then that implies that the area in the tail is less than 0.05. Right? And so you can use either or, but I prefer that you use the p-value approach. Now, our conclusion. Step 4, our conclusion. Still has the same 3 parts, right? Tell me what your p-value is, right? Compare it to the alpha level. Is it less than the alpha level or is it not less than the alpha level? Right? What does that mean in terms of your null hypothesis? Do you have enough evidence to reject H naught or do you not have enough evidence to reject H naught? And then finally, what does that mean in terms of the question? So here we go. Since our one-sided p-value, none of this is new, right? I'm not gathering new knowledge here. I'm just putting together all the knowledge that I've already put down somewhere else, right? I'm just summarizing it. And so you should highlight all those things that you worked for, right? You had to figure out, do I have a one-sided test, right? Or do I need to replicate this area in the upper tail as well if I have a not equal to in my alternative hypothesis, right? And so you've done work there, so you may as well tell me about it. Since our one-sided p-value of 0.179702 is not less than our alpha level of 0.05. And this is where I encourage you to use that phrasing of it either is less than the alpha level or it is not less than the alpha level, because then you'll have that symmetry, right, where you have enough evidence to reject H naught or you do not have enough evidence to reject H naught, right? So if it's not less than the alpha level, then you do not have enough evidence to reject H naught. So which means, or since our one-sided p-value of 0.179702 is not less than our alpha level of 0.05, we do not have enough evidence to reject H naught. That's a good thing in this case, right? We didn't want the dissolved oxygen level to be less than 5. We were concerned that it might be, right? And so if we were really concerned, we should have done what? Taken a bigger sample size, right? For more reliable estimates. Because, wow, it's really getting out of hand here with the theory. What error could we be making? If I don't have enough evidence to reject H naught, the error I could be making is maybe I should be rejecting H naught. I don't know that. That's called a type 2 error, when I fail to reject H naught when I should have rejected it. Okay. And the only way to remedy a type 2, or not the only way, but usually the way to remedy a type 2 error is to collect a bigger sample size. Right? And so that's why I say, well, then you should have collected a bigger sample size. Right? Okay. It all comes together. This means that, and this is where is there evidence that the aquatic life is at risk? No, there is not evidence that the aquatic life is at risk. Whee! Therefore, there is not evidence that the aquatic life is at risk. Whee! Oh, and I've got some important stickers. Whee! Nice. So what is the dissolved oxygen level then? Not significantly less than 5, right? That's all we have been able to establish, and that's all we are able to establish with a hypothesis test. But if we actually want to know what some reasonable values are for the dissolved oxygen level, then we use a confidence interval. Yeah. So or maybe I'll say a confidence interval. If we want to know what a reasonable value for mu, which is the population mean dissolved oxygen level, in this case, that's what mu is representing. So if we want to know what a reasonable value for mu is, we can make a confidence interval. Now we've seen that confidence intervals and hypothesis tests tend to line up, right? Because I'm either 95% confident that I've captured the population mean, or it's off of the hypothesized value, which matches rejecting H naught. Now, we only did a one-sided test, and confidence intervals are symmetric. Yeah? And so what happens is the confidence interval will only match the results of a two-sided test, right? Or if we did a one-sided test here, 0.05 in one tail, right? I'm only concerned with one tail. Then I can put another 0.05 up here if I want my results to match, right? Which means I would be making a 90% confidence interval, right? 5% here, 5% here, leaves 90 in the center. Right? And so for our results to match, I'm not concerned that they wouldn't, but just as a heads up, right? Here, we don't have enough evidence to reject H naught, but if I made my bounds bigger than that, then there's a chance that I would counteract my own statement. So to match a one-sided test with alpha equals 0.05, we can make a 90% confidence interval. We can make a 90% confidence interval. Right? Because what we said was, okay, I've got 0.05 here. That was our scenario. But when I'm making a confidence interval, it has to be symmetric, which means I have 0.05 here, which means I have 0.9 in the center. Why do I care about that? Because here is my T star. Now, somewhat sneakily, we already know what that value is, right? Because it was the critical value if we wanted to use the critical value approach for our hypothesis test. And so negative T star is going to be, because it's on the negative end, we said, well, if I force 0.05, and maybe I'll copy this in here. Right, I get negative 1.76131, which means that this T star is 1.76131. We still have symmetry, and that's cool. This is also where the plus minus comes from in our confidence interval. Right? What's this saying? It's saying to capture the central 90%, I need to move up 1.76131 standard errors, and I need to move down 1.76131 standard errors, which is the formula, right, for a confidence interval. And so the question would go something like this. Construct. I always ask you to make a confidence interval. It's the hypothesis testing. Is there evidence, right? Then you need to kind of talk yourself into it. But construct a 90% confidence interval for the mean dissolved oxygen level of the stream. Right? That's the population. From our formulas, right, we know we have a point estimate, which is going to be X bar, and then plus minus our critical value, which is our T star from up here, S star, times S over root N. Right, that's why we need that T star. It tells us how many standard errors do I need to move out from my sample mean. So our sample mean was 4.77. And I'm going to go up 1.76131 and down 1.76131. And that's why it's plus minus T star. So we use doesn't actually matter if you use the positive or the negative version, because the negative version down here, right, would just turn your plus into a minus and your minus into a plus. Doing the same thing. 1.76131 times the S was 0.94. I think I'll confirm, divided by the root of 15. Let me confirm them. Okay, nice. What's really nice about means type of questions is once you've calculated the standard error, you can store it in your calculator and you can reuse it, right? Because it's the same, unlike proportions, right? Then we have two different standard errors depending on what we're doing. So this kind of streamlines our calculations a little bit. I'll still do it because it's, you know, nothing crazy and I'm worried about space. So I'll give myself one more line. 0.94 divided by the root of 15 is still that 0.2427. I'm going to multiply that by 1.76131. May as well use all the values we can get, which makes my margin of error 0.4274821.893. Which I can store. 4.77 minus that guy. 4.3425178111. Now I've used rounded values, and so as a general rule, you can round to the same number of decimal places that you were given, right? 2 decimal places. And 4.77 plus that little guy up to 5.19748218.9. That's my confidence interval. And now I need to interpret this interval, right? And just like all the other confidence intervals, I am 90% confident that the interval from 4.34 to 5.2 captures the mean dissolved oxygen level of the stream, right? Kind of implying that that's the population. But it's important that your interval or your confidence interval interpretation is about the population mean. We are trying to keep it on this one page, 90% confident the interval from 4.34, notice my lack of units, bad, to 5.2, I think it's milligrams per liter. Captures the mean dissolved oxygen level of the stream. Nice. Now, 5, right? Going back to our hypothesized value, 5 is in this interval. So I'm 90% confident that that's one of the plausible values, right? And the only time I would be concerned is if this whole interval was below 5, right? Then we would have rejected H naught. And so there's symmetry there. All right. That feels like plenty, and also that's it. If you have any questions, let me know. Yeah. Otherwise, enjoy your conference, enjoy your weekend. See you on Tuesday. Yes. And now that we've seen numerical data, I'll introduce it on Tuesday. Thanks, Sabrina. Let's see here.